Morning session, and we begin with Barbara Terhal from Delft, telling us about the Renormalization group decoder for four-dimensional toric codes.
Okay, thank you. So I had to decide what to talk on, and the grid states and GKP states are sort of high interest. So I had some thoughts about talking about that. But this is a more recent result, and the main person who's worked on this and came up with the idea, Casper Duivenvoorde, just left for non-quantum industry. So I thought I'd also honor him for his very nice work by giving a talk about this thing. And so the motivation for the project was basically to address this issue that the toric code is basically the code that has that's the sort of simplest maybe to build, and also has the best threshold as far as we know. Now, this is not quite true because there's this CNIL work which has numerical values that maybe indicate higher thresholds. But why can we not beat this, right? This is kind of annoying. I mean, it's unlikely that this is the best thing. And where should we look for to beat this threshold? And why should we over-focus on a threshold? And I think thresholds are kind of, for a theorist, are kind of like, well, okay, you do some numerics, you get a number, and then next time you give a talk, you even forget the number. I mean, it's like a number, right? It's not very deeply theoretically interesting. But it is, of course, very important, because it is incredibly hard, I think, experimentally, to be below threshold. That's the one thing, at least that's how I always have believed. That's the one thing that we should focus on in the near term, not like how much overhead we have for, gates and so on. But that's just my personal opinion that that threshold is important. So then you can say, well, okay, so we go to more exotic codes, which some people don't even want to hear about because it's way too exotic and weird and so on. But then you can ask, is there any benefit that you get in terms of threshold that would really, so you can make the case for a code be interesting. So we say, okay, blast it with computational power as much as we can, but in a scalable fashion. That's to say, if the code gets larger, I still want an algorithm that is efficient in the size of the code. Otherwise, blasted with power could just be integer programming or something. Okay, so then the question is how you do this. So the 4D toric code, first, I think, discussed in the paper by Dennis and Preskill and Landau and Kiteev, is a good candidate, and we wanted to do this so the 4D toric code has periodic boundaries in 4 dimensions, so it actually encodes 6 logical qubits. And that's just because of the second homology group of the 4 torus is 6-dimensional. And so that's kind of overhead. You say if you want to run a decoding process, you prefer to work with a code that encodes 1 qubit. So that motivated us. I'm only on my first slide, but just giving the whole talk is fine, right? Okay, so that's motivated to define the tesseract code, not to be fancy, but just to kind of say, that's the one with boundaries. And actually what we do in the paper, so maybe my talk, I want to, because it's not that long, I just want to advertise a little bit what's in the paper, because also some of these technical things, you can't absorb them just from a slide. So in the paper, we just define a whole class of, surface code in any dimension that encode a single qubit. So the total dimension is D. And then I have a surface code which has a logical X operator and logical Z operator. And the logical X has, say, D1 dimensional support. And the logical Z operator has D2 dimensional support. And D1 and D2 add up to D. Yeah, so we have I think people know that this, exist. I have also referred to these types of codes, but we kind of are a little bit more precise with the boundaries and showing that you can encode 1 qubit and what the logical operator looks like and so on. Okay, so we kind of generalize, the surface code comes from this using, Rafi Kiteev introduced this was using some relative homology. So one way of describing this is using relative homology. So I'll mention that briefly. Okay, so that's one reason to look at this tesseract code is that it encodes only 1 qubit, so you can focus on the 1 qubit. And there's another reason for it, which has to do with that you can also ask in this 4-dimensional space with periodic boundaries everywhere, are there non-trivial loops that are not the boundary of a surface. And that's the first homology group of the 4 torus, and that turns out to be 4-dimensional. So, and this has an effect I'll come back to make these, there's a single shot decoding process that you define for this code, which would not necessarily work well for the 4D toric code, but does work well for our tesseract code, because for the tesseract code, there are no non-trivial closed loops because of our boundary choice. That's another reason. Okay, so threshold is everything and nothing, in the sense that it's like very important. And then we also hear talks about, well, you know, what about coherent noise? What should be the measure? So, but of course, if we compare codes according to the same standard noise model, threshold is meaningful, right? The fact that these values of these noise thresholds may be changed if we look at a different noise model does not, you know, is independent of this comparison between codes. Yeah, so if you just gather a few numbers, and so we focus in our paper, so there's two, everybody, sort of people worked on decoding knows these, there's these favorite noise models, one in which you say the cinder measurements are perfect, and I just have independent X and Z errors with probability P. Yeah. And the other case is where you say the cinder measurements are noisy, and they also fail with probability P. You could vary this probability to be Q and look at how these things change. But we just take both probabilities to be P. And then there is also work on a gate-based threshold, which we also actually look at. So you can say, okay, now I have my parity check circuits that I have to implement, and every gate in this parity check circuit undergoes depolarizing noise with some error rate P. And so that I refer to as circuit-based or gate-based threshold, and how does things fare then? And so, for example, we get for the 2D surface code, that's this 1% or 0.75 to 1% number, depends on what you do for your decoding. And so, okay, so to start with, I could say that what we get, we do lay out the parity check circuits in the most efficient way. We get 0.3% with our decoder, which is not bad, but lower, and I can tell you why. It's that kind of obvious, it's almost obvious it's lower. But the sort of more positive numbers are sort of here. So what's in white is new results with this decoder. What's in gray is previous upper bounds through various arguments, not all the same argument. But so if we look at this last row, 4D tesseract code, the logic operators are both surfaces for this code. And the RG decoder gets 7.3%. And when it's the measurements are faulty, that reduces to 4.35%, which is not a big drop in the sense that if you do the same thing for the 2D surface code, you go from this is the maximum 11% to 3.3%. And one other thing, oh yeah, and we can also, one more comment to make about sort of advertising. We can also apply, because we can actually apply this decoder on any high-dimensional surface code with surface-like logicals, but I think the decoder could be modified to have, 3-dimensional logicals and things like that. But we can apply this, for example, to the 3D cubic code. So that's the code I think that Dan Brown talked about. It's not the H code, where you have one surface-like logical and one line-like logical. And so for the surface-like logical, our decoder gets 17%. So you see there, it's pretty high, which is consistent with high numbers that have been obtained for 3D color code recently. I'm not sure somebody will talk about this. What more can we say about this? Well, I mean, one thing that I think one can say is that clearly the intuition is that if you have the dimension of the support of the logical operator is 2 or higher, you're much more robust to noise. Right? This is an intuition that comes from self-correction, and we can see some of that from these numbers. I don't know, we can discuss this. Okay, what else do you want to say about this? Yeah, there's these, so this 11% it comes from these studies of these random plaquette gauge, what's it, RP? These studies where this Nishimura line crosses the phase transition and so on. And this is also based on a conjecture by Takeda Nishimura, but it shouldn't be surprising that we don't quite hit this number. Okay, yeah, so that's sort of what I want to cover. Define the tesseract code with a few references to surface code. Then discuss what this renormalization group decoder does. And then make some comments about what I call space-time versus single-shot decoding. So space-time decode, so for the surface code, we always do this. We have, a collection of syndromes, you repeat it, and then you look at a whole, window of them of size scaling with the length of the code, and you decode this, in one go. So you go to one dimension higher to do the decoding. And so we just call this space-time decoding, and that's actually what we look at for this 4D tesseract code. So if the syndrome is perfect, we do decoding in 4D. If the syndrome is not perfect, then we do space-time decoding in 5D. And we can compare that something with single-shot decoding, and they have different. It's not the same threshold, I think. The performance of single-shot decoding is quite a bit, seems to be below this space-time decoding. Okay, and now we have also, I want to come to that at the end. So we have an argument. So we wanted to understand, of course, if this code is of any interest, you say, well, okay, what are the gates that can do efficiently? And there's this promise or hope that once you're in 4 dimensions, you're not restrained by these Bravia-Koenig results. There's more room, because you have the color codes, there's more room to get constant depth logic for non-trivial gates. And I thought first this sort of, would be the case, but now I think it's actually an open question, and we have, for as far as I know, because you don't get this from mapping from the color code, and we have some no-go for some type of way of doing it, which I just want to touch on, which uses these Bravia-Koenig arguments, but it's definitely not an absolute no-go, so I don't want to, make it a sort of a big deal. It's in the appendix in the paper. Okay. Okay, so let's remember that the problem, of course, if you talk about this 4-dimensional code, is that there's not a really good way of understanding it, except for just sort of algebraically saying what objects you're talking about. It's less of an intuition. So we have a hypercubic lattice. There are 4 directions, 4 vectors. And we have, points on this lattice, and they're just 4 coordinates. We can label them like this. And for this code, we label, and I'm not actually using this notation that much, but in the paper we label faces like this. They are located at a point. We have to decide, which point of the face you're choosing for that. And then they have a direction given by 2 out of the 4 directions. And the qubits live on faces. And that's the definition of the code. Now the X-checks of this code are associated with edges. And they are weight 6, because if we're in 3 dimension, it's weight 4, right? They act on 4 faces. And then if you go to the 6th dimension, there's this sort of thinly outlined thing applying, there's a check on 6 faces. So the Z-checks are on the cubes, also weight 6. And I've been trying to promote this term qubit degree, because it's kind of handy, which means that the parity check weights are 6, but every qubit participates in 8 parity checks. And that actually becomes important for this gate-based threshold, because it means that if one qubit participates in 8 parity checks, I have to do at least 8 rounds of C-naughts. And there's sort of, so there's 8 time steps versus this number is 4 for the surface code. So there goes your advantage, basically. Yeah, so the lattice, this is also known, the lattice is self-dual, right? So you can go from the, if you go from faces to faces, similar as what you have in 2D, where if you go to do lattice, you map edges onto edges. And we have also full characterization of the parameters of this code, which is a little counting that you have to do. So what you can see from this expression also that the overhead is a little bit higher, because if you just take sort of the straight up surface code, there's a factor of, this is 2D L squared for L distance of order 2D L squared, and here's a factor of 6. So so we have some concrete numbers of small codes that you could imagine looking at. So this is an example of two surface-like logicals, but then of course to observe what this really says is that you have this logical Z is faces in the 3-4 direction, and I'm summing over all edges in that 3-4 plane. And this sort of attaches at, so I want to talk about boundaries just a second, because there's this notion of smooth and rough boundaries. And that's a little hard to imagine in 4D, right? For the surface code, we have one smooth and one rough boundary. Now, in this tesseract code, we have actually 2 smooth and 2 rough boundaries. And I want to get to that in the next slide. So what I want to say. Well, I just want to summarize that you can just, this is really just a generalization of what Brevi and Giteev did in their paper. And the best way to define these things is to really start with you have a space. So it's everything in that space. There's 4 coordinates, and they run, they run from some value. And there is something you call a boundary space, which is defined as the hyperplanes for which these last coordinates take the terminal values, 0 or 2, right? A boundary is just defined as one of the coordinates takes a terminal value. And in this tesseract code, the boundary is 3-dimensional, right? Just one. And that's we call rough boundaries. So they're 3-dimensional boundaries. Don't try to imagine that one of these coordinates takes a terminal value. And then the way you construct, so you can look at all cells in U. And cells are vertices, edges, and it's just a little piece of edge inside that space, or a cube, or a face, right? And now so that's sort of in the previous slide, these are all kinds of cells, right? These are, and these cells, so cells which are in U, but which are not part in B, which is this boundary. So the boundary is determined by V3 is 0, that's one boundary, and V3 is L is a non-boundary, V4 is 0 or L, other boundaries. So all edges or faces or cubes that are in that B, contained in that boundary, are not objects that I associate qubits or checks by. No. So cells which are in U but not in B are part of the code constructions, you can say. Yeah? So these correspond to edges, cubes, faces, and vertices of the lattices. And so for example, if you just do this in 2D, you have, this is the boundary where this coordinate's either 3 or 0. And so this edge is not part of the lattice. And so this face does not act on that. If I take the boundary of this face, this edge is not included, and this edge does not have a qubit. And that's why we call it a rough boundary there. Yeah? So the point is that you construct, typically if you have closed boundary conditions, you do look at homology, and so you have a cell complex, and you construct boundary maps, right? Mapping from a face to the edges around the face, or from a vertex up. So that's the co-boundary operator going from a vertex to, say, all the edges coming out of the vertex. And then if you use co-homology, you have actually your objects or elements in U, where you modded out B, a quotient space. They call it a quotient space. U mod B, I guess is why you say it. And then you can consider relative homology classes. So one thing is you say, well, we had this construction. You say, how do you prove that it encodes 1 qubit? It's actually not. Well, yeah, you say, well, okay, you just take out how many linear independent stabilizers there are and so on, but you have to check. I mean, it's harder to prove, right, if you just have a visual proof of it. Yeah, but we have actually some argument in the paper that you can use deformation retraction as a more sort of general tool to prove these things. Yeah, of course, we also know numerically that it works, but yeah, anyhow. Okay, so I have a little curiosity, which is kind of a distraction if I want to finish my talk on time. But I just thought, so at some point, you want to understand what's homologically non-trivial. And so, so there is something called, I would call the Klein-Bottle error. And a Klein-Bottle is a closed surface, it's this little thing, that you can embed in 3 dimensions. So you can make it out of like faces in a 3-dimensional cubic lattice. And in 3 dimensions, so if you have your qubits on faces, and there's checks associated with edges, then this Klein-Bottle is a real error, meaning because where the intersection actually happens, like this surface has to be self-intersecting, there you have, there are 3, you see, there are 3 planes meeting, right? So the 3, the error does not commute with the local edge. But actually in 4D, you can embed, so it's known that the Klein-Bottle, I mean, this is actually a depiction of it, the Klein-Bottle, so there's this surface that is, you know, this, the boundary of this box, I hope you can see it, and then the surface goes like this, and it's sort of, you know, in this inner surface. And then now I have to close this tube with this one, and I'm in 3 dimensions, so I just take the 4th dimension and I close it there, right? So I don't have to intersect. So this is just a curiosity. So then this Klein-Bottle error is not a real error. It's actually just it's an element in the stabilizer group. So you can actually construct it from, so imagine this is surface is all z's, and I have cubes which are filled, they have a z surface. I can make this thing from actually filling this with cubes, and also this with cubes, and then filling this outer thing with cubes. So that's just a curiosity. I don't know. Because they say, well, this looks topologically non-trivial, right? But now this is in the stabilizer group. So, yeah. So what is first topologically non-trivial? It depends on the dimension of the space that you're working in. Okay, how am I doing on time? Let me sort of... Okay. Okay, yeah. So I already sort of alluded to this. I'm not using the toric code because I have, there's non-trivial closed loops, yeah, which I don't have this. Now, what is the decoding problem? Now, people have maybe already have an intuition for it, and we tried to do this a little bit more formal in the paper. So I already referred it to these boundary operators. So this is the common notation. There is this del2 boundary operator. The 2 stands for I'm going from a 2-dimensional object to a 1-dimensional object. As for from a face, this is dropped off faces, to edges incident to it. And then there's the co-boundary operator, goes the other direction. This goes from a 1-dimensional object to a 2-dimensional object. And I can also have something that goes from a 0-dimensional object to a higher dimensional object. Yes, so so let's say the syndrome, say we have Z errors, right? Because the whole thing is self-dual, so we just restrict ourselves to one type of error. And the syndrome is picked up by what's on the edges. So there's an error, and if it anti-commutes with the check, which is given like that, it gives a syndrome. And by just using properties of these boundary operators, namely that this is the co-boundary operator, which is the transpose of this operator, this del2, and you can bring it to the other side, you can see that the syndrome is the boundary of an error. Okay, so that's a more formal way. And the other thing is that you can say, if I take the boundary operator of the syndrome, then if I just plug this in here, I get the boundary of the boundary, right? So and that's 0. So applying the boundary operator twice is 0. So that says that the boundary of the syndrome is 0. The syndrome forms closed loops. There's another way of saying this, casting this in a sort of this language, is that if the syndrome forms closed loop, then I can pick at any edge, and I can look at the syndrome on the edges coming out of this edge, and this has to be 0 modulo 2, right? Because the syndrome has to come in and out, or come in and out, even number of times. Yeah, so that's using this thing. Yeah, and so for the tesseract code, any set of closed loop syndrome is due to a set of errors on the faces. And now I want to make this point about why the single-shot decoder is good to apply in this tesseract code, but not, well, for this 4-tor is not necessarily. So when the syndrome is noisy, what we'll just have, the loops won't be closed, right? So this is sort of a depiction. Here I have little missing pieces of loops or additional pieces of loops. And there's the single shot, I call it repair syndrome decoder, which has also been applied to the 3D gauge color code, where you say, okay, I just have a piece of string. I'm going to determine the boundary of these piece of string, right? So just a bunch of points. And I'm just going to do minimum weight matching on these points to close these. Of course, you toss out some information by doing that. So then, if you've done that, you now have closed loops. And then you say, okay, now with those closed loops, I'm going to find a minimal surface corresponding to a lowest weight error that can give you rise to this surface. And so this is a good thing to try for this tesseract code. We also did it in the previous paper for the 4D toric code, I have to say, because we had a previous paper on these codes where we focused on local decoders and getting some thresholds. And this work is more about trying to get the best possible threshold. Okay, so you can compare space-time decoding in 5D with a single-shot decoder. Okay, so now one more thing about the space-time decoding problem. Maybe this is understood. There are other papers, I think by Kovalev and Priatko on more generals, how you generally formalize the space-time decoding for LDPC codes. Okay, but you and there, I think this is some interesting questions. So the minimum weight, so for perfect syndrome, the minimum weight decoding problem is finding a minimal surfeit given its closed boundary in a 4-dimensional hypercubic lattice. Of course, it's not maximum likelihood decoding, but let's focus on minimum weight decoding. And so there is some work that some other people also here know about by Sullivan in 1990 that in 3 dimensions, he describes an algorithm which is efficient finds a minimal surfeit and gives its 1-dimensional boundary. It reduces to a minimal cost circulation network flow problem, which is then. But I have to say, so I just emailed Sergey this morning about it because I do not fully understand this algorithm. I don't understand the proof. So I can't say, oh, yeah, this is solved. Maybe anybody has some deeper insights in this. Because I think it actually would be nice to know whether this really applies here, right? Because it's inefficient. But that's in 3D, and it's a different thing. I don't think it works in 4D. Yeah, so the point is we don't have an efficient algorithm to do this minimum weight decoding of 4D or 5D. That's why we come up with an RG decoder. Okay. Now, the one thing I want to mention is that for the surface code, if you've done this, the space-time decoding, what you do is you say, well, instead of marking where I see a syndrome, I'm going to mark now where the syndrome changes. Yeah, and you get these points, and then you match these points. And similarly, now you can you can define new syndrome, which now you will have errors on faces, which is in the 4D tesseract code, and you will have errors on faces in the time direction, which are measurement errors. And we can do this for any general d-dimensional surface code. You have a construction like that you actually the decoding problem is the same now. Okay, so I'm going to go a little fast through this. We still have closed syndrome. This new syndrome is still closed. You can show this. But the goal is now to find a minimal surface in 5 dimensions. Yeah? And this is sort of an analogy here. Okay, now let's describe the RG decoder. So there are RG decoders. For example, the Braviha decoder works for any topological code. So we could have used this. It's not fine-tuned to the problem at hand, so maybe we would not have gotten the best numbers. I don't know what numbers we could have gotten. Somebody could explore this. There's also the Decoding-Poulin decoder, which is focused on the 2D, the surface code problem. So that doesn't quite apply. Okay, so our decoder has no guarantee to find a minimal surface. It can be implied in any dimension. It could also maybe be tweaked to be more for general syndrome. But the idea is this. So, so it's a coarse graining procedure. I mean, this is just a depiction of it. If this is a piece of syndrome, which is a closed loop, we're trying to find partial corrections, a sequence of corrections that map the syndrome on a more coarse-grained syndrome, which one could imagine, you know, as a syndrome on a smaller lattice. And then we repeat that until we have something that's really small. Yeah. So, so what we say, we have some code of some lattice size L, which is you know, jumping up so there's an n that increases from 1, 2, 3, etc. And there's an edge set EL, and there's a coarse-grained edge set ELCG. So for example, if I look at this little code, which is just a little surface code, there's an edge set, and the coarse-grained edge set is this blue stuff. And the coarse-grained edge set you can see as the image of a smaller code, right? So the mapping is like this edge gets mapped onto this pair, this face gets mapped onto this thing. And so this goes on. So we find a surface such that, so we find a correction, or this is the goal, to find a correction, such that if I take that correction and its boundary plus the actual syndrome, is just part of this coarse-grained lattice. We move the syndrome onto the coarse-grained lattice. And then we deal with that on the coarse-grained lattice. We moved from L to some smaller L. Yeah? But then you can ask, of course, how do you actually solve this first step, right? And we don't really, our decoder is not really, like, I think the decoder by Decoding-Poulin is much more formally saying what's happening with the logical information and so on. Our decoder is just sort of we don't really do a lot of analysis of it, we just apply it. Okay, so Hecky just asked, can I even find a correction such that I move the syndrome on this coarse-grained lattice? Okay, the point is that, of course, this problem is also not necessarily hard, and easy, sorry. So we just solve this by dividing the lattice into small boxes. And a box is something where I say I have a vertex and I have a collection of edges and faces around it. So on those faces I can do a correction, and on those edges I'm looking at the syndrome, and a subset of those edges will be on the coarse-grained lattice. And now I just want to do a correction that moves it onto the coarse-grained lattice of that box. So I'm done for the box, and I want to make sure that the next box I'm taking, of course, doesn't mess up what I've already done. Yeah, so we do that. I don't know whether there's much to say about it in short time. This is some action. Okay, so let's just give you some results. I already stated some numbers. It's too small. So this is threshold numbers for perfect, no errors in the measurements of the syndrome. So that's the 7.3, and these lines are matched to some formula like this, that the logical error rate scales as some constant times p to the b. Actually, there's probably a sign here. So this is the expected, right, it should go with the minus, but you should expect, the distance of this code is L squared. So for the surface code, you have a scaling that goes like d over 2. And the ceiling of that, because it's just the first correct error that you can't correct, basically. So we see a similar, matching. You can match these curves with a similar scaling. This is numbers for the 4.35, so that's the space-time decoding in 5D. And this is gate-based error model, and this is the 3D. So you see 70%. This is the 3D surface code. Okay, so I'm not sure what I can say about these numbers. Yeah, so I want to say something about the single-shot repair syndrome decoding. So, we have had discussions like, does this even have a threshold? But Bombage proved that this is a threshold, so it must have a threshold, so we have to believe Hector on this because it's a bit subtle, and it's also, why. So what I mean by this decoder, of course, there's other ways of maybe doing single-shot error correction, meaning that you only look at correlations in the syndrome over order one time, net scaling with the lattice size. This is just the approach where you just, pair, make from the open loops, you make closed loops, and then you find a minimal surface. And actually what we do is we do this minimum weight matching in 4D to close the loop, and then there's a brute force integer programming all out to get the best surface that corresponds to it. So in a sense, you give it the best chance to get a high threshold. And the numbers here, so this is for these noisy measurement. This is what we're interested in. And I said it was 4.3 for the other decoder, and it was 3.3 maximally for surface code. And here you see it's not extremely clear. There's also some odd even effects, like that the codes, depending on whether the L is even or odd, it does better. But it's definitely below 3%. But we also apply, maybe this is sort of a little bit cleaner, we just apply the same thing for the 2D Ising model, right? 2D Ising model, surface-like thing. You have little loops that are just bubbles of errors, and if you have noisy syndrome information, they're open loops. You can apply the same idea, and then you get, a threshold which is in the 10 to 20% range. Okay. Now, one thing I want to say about this single shot and about this, so I have the feeling that this single shot is really a different phase. If you were doing this on a StatMech model, it's a different phase transition. As far as I know, I'm not sure people know how to write this down or to evaluate what this optimal threshold corresponding to this phase transition is. And there's also a point with, so the single shot method, you also have to be careful. You cannot correct errors of weight order L, and I just show you, of course, maybe this is not the typical error that I'm going to show, but I just want to give you some argument. Of course, the code should be correcting errors of order L squared, right? So this is not so good. And we've called this previously energy barrier limited decoding. I'm not sure it's so applicable here, but anyhow, so let's imagine, this is sort of a picture where, let's imagine you have a piece of string which kind of extends over the whole lattice, and it's broken up. And then, so you have to match these points, and then you do that in the wrong way. And this is also what happens in the surface code when you're sort of below threshold. You start matching to the complement of the string of the error that really happened, and you make a logical. And in this case, you'd make some string that connects the whole boundary. And then if you have that as your syndrome, you say, okay, well, there's a surface on this side that's attached to the boundary there that's responsible for this syndrome. And that surface could be, more than, now you make a big error on that, right? Because if the string is somewhere in the bulk, it could be half the lattice on this side. So if you were to read out your memory, now you have an error corresponding to this, and you may not be able to correct it. This is a very hand-waving argument, and so we don't know, yes. But the feeling, and maybe this is already shared by other people, is that the single-shot repair syndrome decoding is limited by actually this first process where you only pick these endpoints of the strings and you try to pair them up. And when you start making a logical error, which it means is when a four-dimensional code which has a line-like logical starts to fail, that's maybe when you also expect this process to fail. So that would, and this is conjecture, I don't know, that would suggest that this single-shot syndrome is bound by sort of the maximum likelihood decoding of a line-like logical in 4D. And that's typically lower than a surface-like logical in 5D, which is what we do for the space-time decoding. Yeah, so that's just coming from sort of trying to understand. I mean, I think it would be nice to really work out this, yeah, to do more theory about this. Anyhow, so there's another discussion that we had about, I said, well, you know, there's like 4D, we're sort of above the critical dimension. Shouldn't it be that if you just do the space-time method, but you only look at the syndrome for order 1 time, right? So you could say, well, I look at time windows of size L, and I move this window up if I'm doing active decoding. But now, because I'm in such high dimension, I can make this window of order 1 size. And that really is not a good idea. Casper tried to implement this a little bit, didn't get very good results. And there's sort of the intuition is that it's the same problem that you have for the surface code, which is like, imagine that an error patch, just real qubit errors happens. That's sort of this red thing. And you see that as a loop of syndrome. And of course, the length of this loop is smaller if the patch is large than the volume, right? So if the loop is large enough and you only look at it for 1 moment in time, you say, well, it's just syndrome error. If you just do a process where you pick the minimum weight error that corresponds to this. And so if you extend this, so the point is that if you just extend this for constant in time, okay, so you make this a little thicker, you make this boundary t times, the boundary at 1 point in time. But if a t is order 1, then if v scales with L, then this is still not working. Yeah, so, but, okay. Okay, so then there was this thing that I said about the back of the envelope. So why is this threshold for the gate-based model worse? And you just do something like, what's the effective ZR rate on a qubit during a QEC cycle? There are 8 C0s, and there's 1 time step for measurement of preparation. So you can look at the polarizing rate pre. There's a probability for the ZR near C0 is given by this, and that's total 5.6 times P. Let's say that's the effective ZR rate. That should be, no more than 4.35%, which is what we get before. So that gives something like this. Yeah. Okay. So how much? Done. Okay. 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 Let me just say one thing about this. I'm not going to the argument. So the only argument that we have is we can only do restricted Clifford gates if we take copies of the tesseract code and we restrict our constant depth circuit to be such that it is local if I glue together these copies, or if I allow the neighborhood of a qubit in this tesseract code be the neighborhood of its partner qubit here. So I don't allow any rotations of these different codes. If you want to know more about this, you should ask me. Okay. Yeah, that's, well, whatever. Questions, maybe.
Thank you, Barbara. So we can take a couple quick questions, maybe.
So I like that this is outside the box thinking. It's inside the hypercube still, but so my question is there any way that you can take advantage of the nominal sense of self-correcting memories in your decoder? It seems a little bit like that's not showing up here somehow.
Well, no, it's not. Well, it's showing up. In fact, that you can do single-shot error correction, that you expect a threshold, but the threshold may be dominated, maybe not good enough, right? So that's maybe the point, that you can do single-shot error correction here, which you can't do for the surface code. And the fact that you have a surface-like logical also does make you less sensitive to this having syndrome noise. The point is that our decoder now goes from 7 to 4%. So I don't know how much you can boost these numbers, but the numbers, 4% is definitely higher than for the surface code. So I do think there's an effect of self-correction, but it's kind of masked by how good is this decoder, can we get better? I mean, the point is really this 3-dimension may be the sweet spot, right? If you go to too high dimensions, the decoding problem gets too hard. Low dimensions, you don't have self-correction and not easy logic, and yeah, there's a lot of constraint. I know. Yeah. Yeah.
Okay, let's see. So regarding the single shot, nobody says that you only should think in terms, so when you are talking about errors of order, like if you are more imaginative, maybe you would think that you can think not only of measurement errors and correct measurement errors in themselves, but be thinking at the same time of what is the probability, for that thing to appear, taking into account the actual errors. Then if you want to think in terms of like order one, like error correction, like for some order one time, as I told you personally, it would make sense to apply single shot ideas because that's the regime where you are working. And finally, you don't need to believe me because you can read my paper. And if it is wrong, you tell me.
No, I believe you. But the thing is that the point is you say, okay, I only care about, if I do my correction, that I have a manageable error distribution on the output. I don't need to correct all errors. I understand that point, yes? But it's hard to say what you're actually going to do then. We did this Tomes rule decoder before, and we did other decoders. And thresholds are just not so good. So I think the only point I'm trying to make is that single shot works, but you get those 4% number with single shot, right? That's harder. Yeah, okay, yeah.
Hello.
Yeah.
I've been told to be quick, so I'll be as quick as I can. So the thing that was most surprising to me was that for the phenomenological noise model, in the space-time picture, you get something that's bigger than even the surface code, but then you lose that advantage because the syndrome's difficult to read out. So have you considered looking at other ways of extracting the syndrome, like taking 2 copies of the code and doing transversal knots and measuring everywhere or something like that?
No, but I think, it depends really on the platform, right? If you have ion trap qubits, or you could do gates faster or high parity, not do the controlled P gate in terms of 8C knots or something faster, then you do indeed not suffer from this. But, okay, so there are 2 things. There's qubit degree, there's qubit degree and parity check weight. So for some architecture, parity check weight can be higher because you're kind of doing, non-local gates. But qubit degree is not, you can't, so you have to, what I would like to have is a code that reduces the qubit degree and maybe increases the parity check weight. So we've thought about how you can concatenate it with a small code, then like a 422 code. But I don't know, it depends then on platform, right? And what your error model is. So. Yeah, sure.
So it's related to this question of the weight of the parity checks. I'm wondering if the phenomenological noise is a good model to compare different families of codes. Even if we compare, for instance, the toric code with hexagonal color codes, we assume that there is the same priority to flip a measurement outcome as an error in a qubit. And when we measure weight 6 operators, or weight 8 or even more, it seems that it gives an unfair advantage to this kind of code.
I agree, yes. But it's coming from theoretically wanted to maybe say something about it too analytically, right? Or with this mapping on statistical physics model.
So will there be a physically motivated model where the priority to flip depends on the weight?
Yeah, I mean, that's what, I agree, but the point is, I think at the end of the day, it's better just to sort of say, okay, I got this maybe platform, ion trap qubits or something, and what's a reasonable error model then to put in, and then simulate that. Because that's then the relevant question, right? Because,
Okay, I think, well, in
sorry.
interest of time, I think we should move on to the next speaker. So let's thank Barbara. The next speaker is Austin Fowler from Google, who will be telling us about towards a sufficiently fast quantum error correction.